My name is Dr. KCH Apparao, working as an associate professor in mechanical engineering department. Today, I would like to explain on critical thinking on particularly critical radius of initiation. It is very important topic. We'll see this topic first, and we'll see the different numericals which are based upon this topic. So, which are given in the question bank. So, theory question and that related numericals also. We'll see. First of all, we'll see what is critical thickness of insulation. So this one is the question. What is critical thickness of insulation and small diameter wire or pipe? Explain its physical significance. So first of all, we'll see the what is critical thickness of insulation. We know that for this slab, suppose this is slab. If you add the thickness of this slab, you know that the rate of heat transfer Q value will be decreases, because you know the formula for the rate of heat transfer Q is equal to Ka into temperature difference T1 minus T2 by L. So L is the thickness of material. If the L value increases, automatically Q value will be decreases. So because Q is indirectly proportional to L, or L is indirectly proportional to Q. If the thickness increases in case of these slabs, automatically the rate of heat transfer will be decreases. So this is the common thing. Okay. So, but in case of cylinders, so it is in opposite. In the case of this cylinder, suppose this is a hollow cylinder. This is the inside radius Ri. This one is the outside radius R0. If you increase the R0 value, so automatically heat transfer rate Q should be decreased. But in case of this cylindrical and the spherical coordinate system, this rate of heat transfer is increasing to up to certain level, then it will be decreasing. You will see why it is in increasing, then it will be decreases. It would be decreases. We'll see. Okay. Because what is the reason behind this one? The reason is the more a decrease in convection resistance. If you increase the R0, decrease in the convection resistance. Here we will see two types of the resistances. One is the conduction resistance. Another, suppose this is the insulating material. This is the outer radius of the insulating material. If you increase the R0 value, heat conduction takes place from the inner surface to outer surface. Here we will see two types of resistances, or two types of heat transfer modes. One is the conduction mode here in the insulating material. Another one is the convection resistance, that is the from outer surface of the insulating materials to ambient temperature. Okay, so one is the convection resistance, another one is the conduction resistance. But due to increase of R0, the convection resistance value also will be increases due to, so it means if you increase the R0 value, convection resistance value decreases. It means R0, if you increase the R0 value, convection resistance of the insulating material resistance, it will be decreases. Okay, so because of the resistance decreases, automatically rate of heat transfer will be increases. Okay, so this is the reason. We will see mathematically what is the reason behind this one. So we will see what is the theory here. Moreover, in some cases, a decrease in the convection resistance due to the increase in the surface area. It means R0. Okay, so can be more important than increase in the conduction resistance. Here, conduction resistance also there, convection resistance also there, but impact of convection resistance is very high compared to conduction resistance. We'll see what is the reason behind that. As a result of resistances may actually decreasing, resulting in increasing. So because of the resistance, the Q should be decreased, but in case of by decreasing the convection resistance, the Q will be increases. We'll see what is this one. Okay. Here, just to, this is the insulating material. Heat transfer takes place in the insulating material through conduction. Then insulating materials to outer surface. So this is the convection process. So one is the conduction process, another one is the convection process. Okay. Two types of modes are used to transfer the heat from insulating materials to ambient temperature, ambient to atmospheric conditions. The radius up to which, here we'll see. So in the case of cylinders and slabs, if you are increasing the radius like this one, so up to certain level, Q will be increases at particular point. Q is the maximum. Then the rate of heat transfer Q will be decreases. This point is called here at this point the radius of that insulating material for this point, that is called critical thickness of radius or critical radius of insulation. You have to say this one. The radius up to which heat flow increases, after which heat flow decreases. Up to certain radius level, heat will be increases. Rate of heat transfer will be increases. After that, rate of heat transfer will be decreases. So that particular point, so the corresponding, the associate radius to that point, that is called critical radius of insulation, is depend upon the thermal conductivity of the insulation K and the convection heat transfer coefficient K. The final formula R3, critical radius of insulation is equal to thermal conductivity by heat transfer coefficient H. This is the formula. We will derive this one. How to so how to get this one? Just like we see here. You already saw that one. Heat transfer from insulating materials to uh, atmospheric conditions. It means ambient temperature. But so here two types of resistance we will see. This one also you can consider composite to. Uh, okay, no need to take this one. Just heat transfer rate Q by A, Q or Q by A is equal to initial temperature. Initial temperature here you can see initial temperature is equal to T1. This is the temperature T1. So this one is the temperature, ambient temperature T infinity. Okay. So initial temperature T1 minus so ambient temperature T infinity by thermal resistance with respect to conduction plus thermal resistance with respect to convection. It means heat conduction in this insulating material, convection from this outer surface to ambient air or atmospheric air. You see thermal resistances. So here rate of heat transfer Q is equal to uh, so Q is equal to, this is the formula. This is the conduction thermal resistance. This is the uh, convection thermal resistances. So R naught is equal to convection thermal resistance is equal to 1 by HA. A is equal to 2 by R naught into L into H. Okay. So R insulation means so conduction resistance. Conduction resistance R insulation is equal to Ln R naught by Ri by 2 pi Kl. Okay. This is the uh, two resistances. Then according to composite slab, you know the formula Q is equal to initial temperature minus final temperature by all the thermal resistances. Thermal resistance of conduction, thermal resistance of the convection. So T1 minus T infinity by ln r naught by ri by 2 pi kl into 1 by 2 pi r naught lh. So this is the value. So here just you can observe this one. Okay. So here this is the conduction resistance, this is the convection resistance. If you increase R naught, thermal resistance of the conduction will be increases. Okay, thermal resistance of the conduction will be increases. But if you increase R naught value, convection resistance, thermal resistance of the convection resistance should be decreases because it is 1 by R naught. Okay, but here conduction resistance ln of R naught, logarithmic of R naught increasing. This is the direct R naught. So ln of R naught is increasing condition. 1 by R naught is the decreasing condition. If you consider logarithmic means the value is very less compared to this one. So based upon this one, this R naught increases value is very less compared to R naught's decreasing value. So because of this one, the convection, the resistance due to convection is higher to resistance due to conduction. So here convection resistance of the convection is decreasing. Here resistance of the conduction is increasing, but increasing value is very less to decreasing value. So due to this resistance decrease, the Q value will be increases. So up to certain level, Q increases. After that, it should be decreases. Okay. At this point, the corresponding value of R naught, that is called the critical radius of insulation. Okay. So dq by dr naught is equal to T1 minus T infinity. So at particular point, maximum means if you derivative this one dq with respect to dr naught is equal to 0, you will get the maximum point. Okay. At that maximum point, you can get the R naught value. So if you derive this one, it means dq by dr naught is equal to, if you derive this one, you will get this formula. So here dq by dr naught is equal to 0 means this is the 0. If you solve this one, R naught is equal to k by h. So this R naught is nothing but RC, critical radius of insulation. Okay. The final formula for the critical radius of insulation is equal to thermal conductivity by H, heat transfer coefficient. Okay. So this is the formula. Based upon the formula, you can solve the different numericals. The first one is the steam pipe 10 mm ID and 11 centimeter OD is covered with insulating materials. That is the thermal conductivity. The steam pipe ambient temperature and both the temperatures also given. So if the convective heat transfer coefficient between the insulation temperature and the air, so that is the 8. It means H value 8 given watt per meter square Kelvin, and thermal conductivity K is equal to 1 watt per meter Kelvin. So the values are given. If you know the K and H, you can find out the RC. RC is equal to K by H, that is equal to 12.5 centimeters. Okay, or 0.0125 meters. You know this one. Okay, so this is the critical radius of uh, critical radius of thickness, critical radius of insulation RC. Okay, so for this value R naught, calculate the heat loss. First of all, you have to find out the heat losses. For taking R naught as RC, R naught is equal to RC. RC is equal to 0.0125. In place of R naught, you can take the RC, then you can find out the Q by L. Q by L is equal to temperature difference 200 minus 20. Steam temperature to ambient temperature, initial temperature, final temperature, ln R naught by Ri. R naught is equal to 12.5. So that is the RC. Here R naught is nothing but RC by Ri, 2 pi KL. So K is equal to 1, L is equal to 1 also. If you solve this one, then 1 by 2 pi, 2 pi R naught RC L. RT, RCH. So this is the 2 pi, this is the RC, this is the H. Okay. If you substitute all the values, you will get the Q by L value. Okay, so by using the Q by L, you can find out the outside temperature of the steam pipe also. Here, Q by L is equal to only one thermal resistance you can find out, outside temperature of the steam pipe to uh, ambient temperature T infinity by convection process 1 by 2 pi RC into H. If you substitute the values, and you can find out the uh, temperatures, that is the 118.0.72. Okay, so we'll see one more numerical, that is the wire of 6 mm diameter, so with 2 mm thick. Okay, so that is the insulating material. Thermal conductivity. Thermal conductivity also given. If the convective heat transfer coefficient between the insulating surface and air, so that is the H value also given. D1 is given. It means R1 is equal to given. R2 is equal to R1 plus thickness of the insulation also given. H value, K value also given, H value also given. Then you can find out the rate of heat transfer. Okay, so heat flow, rate of heat transfer. So heat flow through insulating pipe when the critical radius is given. So here RC is equal to R naught. Then you can find out the 2 pi L into TA minus dV by ln R naught by R into K 1 by K. This is the formula. Based upon the formula, you can substitute the values. Then you can find out the Q value. Okay. So here, just like we are finding the Q1 value. So when R naught is equal to R naught, okay, what is the given in the numerical, then we have to find out the Q2. Here R naught is equal to RC, critical radius of insulation. Okay, so by finding these two then values, then you can find out the increase and decreasing of rate of heat transfer. So you can find out, so that is the percentage of increase in heat flow by using the critical radius of thickness. If you use that, this value, the increasing value is equal to 0.55 percentage. Okay, so in this way, just like Q1 value here, this is the Q2 value here. If you find out the value, you will get this one. So these are the numericals which are based upon the critical radius of insulation. So these are the, just like different textbooks are given, you can refer this one. So thank you listening this class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.